Okay, PCA. So this stands for principal component analysis. So why do we need principal component analysis? So these are the reasons. First is dimensionality reduction. So you have like 100 dimension data, right? So you have to reduce it to lower dimension. Why do you need to reduce it? It can, help you visualize better. It can get rid of redundant dimensions, okay, and so on. Another is, you have to reduce your noise, right? So you can reduce the uh, yeah, as I said, irrelevant features and irrelevant dimensions you have to reduce, and that will reduce your noise. So even there are some signals, even as coming from brain signals, ECGs, to to even astrophysical signals, astronomical signals, and so on. Whenever you have signals, you will have some noise component to it, right? So this PCA is a very powerful tool to denoise the signal, right? And it has been used in many applications, right? And this visualization, as I said, lower dimensional data is easy to visualize. So you can like plot a two-dimensional graph easily on your two-dimensional paper or anything, but you cannot visualize a 100-dimensional data, right? Feature engineering. Again, you have to remove the redundant features. You have to remove the features which are not very significant in your prediction. And overfitting problem. Again, so as I said, if you are using more and more features, you are basically overfitting your data, right? You are whereas that will cause very high variance. To get rid of that high variance, you have to reduce the dimension of your data, and you can then get rid of variance problem. Again, data compression, this will also reduce the size of your data, and make the algorithm faster, and so on, reduce the computational cost, and so on. Okay, some of the terminologies that are associated with PCA. Yeah, so I will quickly go to my notebook and let me see. Okay. I will explain some of the things. Okay. Sum of squared distances, variance, eigenvectors. Okay, so I will basically, explain what this each of the term means. Okay. Okay. So let's say this is your x1 and x2. These are, let's start with 3 points. Okay. This is your x1, x2. Now you want to reduce this 2 dimension to 1 dimension. You draw a line, and these are the perpendicular distances to the lines, all for all the 3 points. Let's say this is d1, d2, d3. So your sum of squared distances, or SSD, is d1 square plus d2 square plus d3 square. Now you look for the line which has the minimum SSD, right? Okay. Now this is SSD. Now what is variance? So you see, so variance is basically how far are these points from origin. So if you look at this figure, okay, so you see the variance is measured as this. So how far are these points from this? How far spread across are these points? Okay. So for example, so after you have drawn the best fit line, what you do is you project these points on this line. So this will be a projection of this will be a projection of this will be a projection of this. Now what you do is you rotate this line, and again I'm just plotting the same line with the same points. Okay. And now this is your 1D data, which has been reduced from 2D to 1D. So this is your representation in 1D. And your variance is how far across spread is the other points in this new dimension of data. So this is your variance. Okay. So basically, minimizing your square sum of square distances is equal to maximizing your variance, right? So you're basically trying to see which is the maximum variance that you can get from this line. So if you are minimizing this distance, you're basically maximizing this distance. Okay, right? These two are equivalent. Okay. And how they are equivalent. So I think you all know about Pythagoras theorem. So you see this is the hypotenuse, right? This is the height, this is the base. So if you are minimizing the this thing squared of some distances, then you have to maximize this thing, right? So lowering this, keeping this hypotenuse constant is basically increasing this thing. So this is the hypotenuse, this is the height, perpendicular. Let's say this is the base. So hypotenuse square equals to perpendicular square plus base square. So if you are minimizing the perpendicular, right? So keeping this constant, if you are minimizing this has to increase. This will be maximized. So these two are equivalent criteria, right? So basically, what you're doing is minimizing SSD and maximizing variance. Okay. So what is the third terminology? Let's see. So third terminology is eigenvector. Okay. So eigenvector is, so if you see from here, right? So what we are doing actually, so if you are familiar with linear algebra, it is good. But if you are not, what we are doing is, we are taking a part of x1 dimension and a part of x2 dimension to create this new dimension. Okay. So let's say uh, let's say in constructing this vector, you are going a little bit towards this side, let's say zero point 0.5 units towards x1 axis, and let's say zero point 0.8 units towards y1 axis. So 0.5 x1 plus 0.8 x2, that will be your new x axis. Okay. So your eigenvector would be basically 0.5, 0.8. So this is your new vector. Okay. This is how. Okay, sorry, I'm not sharing the screen. Yeah, extremely sorry. Okay. Yeah, so as I was saying, in constructing this new vector, you're going zero point 0.5 towards x1 direction, 0.8 towards y1 x2 direction, and so you're getting the new vector over here. So that's how you get the eigenvector. Your 0.5, 0.8 is your new eigenvector. Okay. Uh, yeah. So that is the next terminology is eigenvalues, loading scores, eigenvalues. So these I will skip. Scree plots. Okay, so these I will explain while I am doing this.